Okay, going live. Ladies and gentlemen, MrCropper here with the Wolfram Hangout on Monday night. We are going to be discussing Stephen Wolfram's New Kind of Science. I'll be doing a lot of it from memory. I've watched a lot of videos, and of course I have the internet at my fingertips. But we will be discussing what the meaning of his work is. And so I want to say a few things before or as people join us about what his work, how I understand his work, what I think it means, what I think the future holds for his work, and what he means by a new kind of science. So settle in and let us discuss this. If you want to join, you can click the link on the far right. You can also go to Facebook and look me up, and I'm on Facebook, and my thing has at the top of it this announcement of this thing. So if you want to join and don't know how, I don't know, go on Facebook and I don't know, message me or something. We'll get you on, or we'll see what we can do. I'll send you the link. All right, so we're going to discuss his book, The New Kind of Science. He calls it his seminal work. I think that it's very important, and I have told that other scientists did this work before, and other theorists noticed these things before, and he sort of comes at it not knowing what other people have done. The book was not peer-reviewed. It was published without, sort of letting the community that would be concerned with it look over it and say whatever they want to say. So I have to say the controversy about this reminds me a lot about Ayn Rand. She was really torn apart because she didn't come up through academia or in academia or concerned with academia, and so they said her ideas are old. She's gathered up some ideas from real philosophers and thinkers and rehashed them and stuck them together under her label. You know, selfishness. Oh, that's Nietzsche. And free economics. Who hasn't done that? John Stuart Mill did free economics, and Jean-Baptiste Say. We don't need to go any further than that. We get free economics from somebody. Ayn Rand gets it, sticks her label on it. So did Ayn Rand do anything original? You know, that's up to you to decide. I think she's one of the most important thinkers in history. So Wolfram, I don't know. I'm not sure. But what seems strange is that these people would come out of the woodwork after Wolfram has announced, hey, this is an important bag of stuff here, and say, oh no, we knew about this stuff all along. Did you? How long were you going to keep it secret? Why didn't you announce it to the world? Why did you think that it was a secret concern of computer science only? Wolfram has noticed it and has come out and told everybody about it and said, by the way, this could change everything. And they say, oh, that's nothing important. We knew it could change everything before. Well, really, there's two options. You did know, and you kept it a secret for some strange reason, or you didn't know. You didn't quite grasp. You didn't quite understand the significance. So that's my view of the controversy about what Wolfram has done. It's not very original of them to say, we already knew about this stuff that this very highly original thinker thinks he's inventing here. So I think that's disingenuous. Now, what do I think is important about Wolfram's work? Let me just check my links real quick to see if I have anybody saying anything about how they want to join or anything. So, Stephen Wolfram's work, let us dive in then. We can talk about what, let's talk about what he did that he noticed his phenomenon in. And I want to be quick about this because it's a little bit sort of boring, but here's what's interesting about it. He wrote these really simple rules. The black square at the top will turn white on the next step if the square next to it on the left and the right is black, but not otherwise. Things like this. And then he starts it out, and some of the rules terminate very quickly. Some of them terminate in 5, some in 20, some in 100 steps. Some of them go on and on. Rule number 30, and it's a very simple rule. It's just that the dots will do this on this step and that on that step. Very simple rule. Produced an enormous and, for all intents and purposes, a non-finite cascade. Now, the middle column of that was, for all intents and purposes, random. And they used it for 20 years as a random number generator. The middle column of rule number 30. Cellular automaton, it's called, because each cell updates by its own rules independent of other cells, or dependent on the other cells. So he found a random number generator in an extremely simple program. Now, that's fascinating, but some of the other programs, like, I don't know which one it was, number 67 or whatever, could produce these cascading patterns that they're not similar to mollusk shell patterns. They are identical to mollusk shell patterns. So here mollusk shell patterns are always different from each other, and yet all virtually the same sort of thing, these different within species and stuff. And we can reproduce them. Not exactly, but we can reproduce the mechanism that seems to produce them in Rule 67 or whichever one it is. It's like fractals, where fractals show us what plant life and so on, what shape plant life and so on do. It's like fractals, but it's in a linear way. Now, what's amazing about the cellular automaton is the fact that very, very simple rules can produce complexity, enormous complexity. That's a surprise to some people. That was a surprise to me. Now, that gives us suddenly the option that things like evolution are very, very simple at root. So simple that they can, fit on one molecule bumping another. That can begin some cascade of truths, which is very, very complex and can't be reduced. So if that's true, then we have a lot of things in this universe that we don't have to agonize over and wonder why and wonder what and wonder where they came from. The metaphysical nature of our universe is such that very small, simple things can lead to very complex facts in the long run. All right, well, it's very good that I have 5 viewers. I was wondering if I might have some people join on, though. Let me try again with this link. I'm going to click it in the side here. And I know that a lot of you are viewing on YouTube, but I am not allowed to view this on YouTube while I'm streaming live, because it would probably create an amazing short circuit and the internet would explode or something like that. So, all right. Now, Wolfram explains random number generation, or provides a case of random number generation. That's interesting with this cellular automaton. What else can it do? Where else can it go? Well, here's the thing that he notices about this, is that there's basically a flow chart in the universe of programs. And those programs may or may not constitute basically the entirety of reality, and we can reach out and sample them. And with computation power that we have today, they actually can sample bits of programs and hand them to you and say, this meets the criteria of being close to this tempo for this style of music. And they can bring you a piece of music out of the computational universe. You can write music yourself, or you can sit there and click and listen to little bits of music that are just out of the computational universe. Now, axiom sets in mathematics are something which can be done in Wolfram's work on a flow chart of reality. And the axiom sets that are true line up in basically a random pattern. What kind of random pattern? So there is a very, very important work to do, even in higher mathematics and such, on taking this seriously. That this is like discovering Darwinism, except Darwinism is like 2.0 and we discovered it first, which is kind of weird. Reality followed a Darwinism 1.0, and bits of reality did things that changed the bits of reality touching them over time, and that's the universe we find ourselves in today. And in what fashion do those changes occur? Now we'll discuss briefly what the second law of thermodynamics has to say about it, or how it addresses it. And this is kind of why I wanted other people to be joining me here, because I've studied physics on my own, and I've only taken one sort of college level course back in high school that you had to be a high achiever to take the course. And I haven't done a lot of physics, so I'd like someone here to discuss these things who knows more about it than me. But the second law of thermodynamics says that heat will always travel from a hot body to a cold body. If you want it in a more abstract sense, heat will always flow downhill. A battery, the universe is a battery which will slowly run out. It's a quote unquote for isolated systems, but the universe is an isolated system. So over 99 trillion years and then some, what will happen? And the water will have all run downhill, so to speak, and all of the energy will have dissipated and become more random than it is now. Why is there any hope offered? There's not any hope offered with Wolfram's work. What he explains to us is how we can have order inside the universe in the meantime. Evolution sort of explains it, but evolution still leaves open the questions of the metaphysical nature of the fact that evolution occurred. Did life occur as like a 1 in a quadrillion trillion chance? Or is it actually something that's potentially pretty common given basic ingredients? Because it's based on some really simple rule that all it takes is these 5 or 9 chemicals in the same area, and they'll bump against each other and things will happen. Is it that simple? Because if it's that simple, then there are serious implications for what we should consider life to be and how often we're going to find it. Let's see. Let me check my links and stuff again and just clear my throat. Thank you for tuning in. I wish I did have someone to tune on and discuss it with me, but if I do have to do it alone, that's all right. I can do this. So what I'm going to do is I'm going to go back and forth a little bit with Wolfram, and I will let him say something, and then I will talk to it for just a moment. And so I have a talk on by the SETI talks about SETI and Wolfram speaking. So I'll let him go a bit, and then I'll address what he's saying there.
Sort of a 300-year-old story, is you use mathematical equations to make models of how the world works. That was sort of the idea of Galileo, Newton, etc., etc., etc. And that idea has brought us lots of important science and technology and engineering and so on. But there's still plenty of areas of the natural world, for example, where we don't know. We don't have a way to kind of explain the kind of complexity and structure that we see. So I was interested in how can we explain these things, and that got me into kind of generalizing the notion of mathematical models and asking what's the sort of more general category of thing that's kind of like a mathematical model, but but doesn't just involve derivatives and integrals and exponentials and things like that. It involves some way of specifying rules for how a system works, but they're not necessarily rules that come from mathematics. And that got me into thinking about, okay, what about using programs as the way to sort of define models of things in the world? Well, then the question is, okay, so if there are programs that define models for things in the world, what kinds of programs might those be? What are the programs that might be behind systems in nature? Well, the programs we write tend to be these long, complicated things. You know, longest thing I've created is probably Wolfram languages, maybe 30 or 40 million lines of high-level code and so on. Big, complicated thing. The question is, what happens when you just think about sort of the simplest possible programs that you can construct? And so I got interested in what do the sort of the simplest possible programs do? So here's an example of one of my all-time favorite types of programs. This is a program as a cellular automaton, and the way it works is it just has a line of cells. Each one is either black or white, and on a series of steps, it just determines the color of a cell based on the colors of the cells above it and to its left and right. So you can sort of summarize the rule for this by saying that that icon at the bottom is kind of the program for this picture that says, given that there's a triple of cells with these colors, what will the cell on the next step be?
Okay, there's a very simple rule that just says both of the squares will turn black if there's a black square. So then you go to the next one, and there is a black square on that one, so therefore two of them turn black, and that's a not very interesting rule. Down here you see a display of the rules. Now we'll skip ahead a little bit to this one, which is the one that it has a random number generator down the middle.
Random generator in Mathematica and Wolfram language for about 25 years. It was retired recently because we found one that's more efficient. So for all practical, even though the rule is really simple, if you see that center column there, it seems for all practical purposes random. So when I first discovered this back in 1984 or so, I spent a bunch of time trying to figure out, could I use some fancy mathematical analysis techniques, some statistical analysis, cryptanalysis, all these kinds of things to crack this, to figure out, if I just saw that sequence, could I tell that it came from a simple rule? And my conclusion was I couldn't figure out how to do that. And so that kind of got me started on realizing that, yes, in this computational universe, there are lots of simple rules that...
Okay, so let's talk about that for a second. That's interesting that he noticed that a simple rule, not only a simple rule, but a really, really simple rule, eventually led to observable randomness, but immediately led to observable randomness. That is interesting and amazing, and I think that it's an important thing for us to notice. It takes a lot of burden off when we try to describe how things become complicated. It's a lot less difficult to imagine a situation or a process that would lead to complexity. So you're a lot less tempted to go with the magical man in the sky, putting everything together. Super Fin Guy has joined us. Sir,
hello.
Where did you get the link that was successful to bring you up here?
Well, first I looked on Google Plus and I didn't find it there. I went to Facebook and I found it.
Okay, good deal. So the one on Facebook is appropriate and useful. Very
yeah,
good.
anyone that wants to join, head over to the Facebook page and the link is there.
Awesome. All right. Well, I've been speaking my head off waiting for someone to come on. I've explained to the ladies and gentlemen cellular automaton, the random number generator, and Rule 30. Do you want to say what, if anything, what have you read of Wolfram's? Just give us a heads up of where you're at with it.
Well, the first time I heard of him was in about 2008 or something. That I saw a couple of videos of him, and the videos that I saw, he was explaining the sort of like the cellular automata, the sort of like fractal, rules that grow and grow. I saw that video, and I didn't get much from it. And then a couple of days, I saw other videos of him. And I took some notes on some points that I would like to make later on his findings. Yeah.
All right.
Yeah, and
So no, so do you said you didn't really get too much from his talk on cellular automaton. So what do you think is important in his work, or where are you
well,
at?
well, I also think that his cellular automata. I think it's important. I think that it shows it's equivalent to a lot of sequences that we see in nature. For example, the Fibonacci sequence. It's one simple rule that grows into complexities like the Fibonacci spiral and stuff. Yeah, so it's basically a fractal system. You could take his functions and plot it in a in a program, in a plotting program. You know, so that's interesting. And also because from what I know about the universe, it seems like a fractal universe too. We go from things in everyday life to the molecular level to the atomic level and beyond, because I think that matter cannot end at one point, because that wouldn't make sense, because something has everything has a composition. It cannot be like uncomposed, if you will. Yeah, I got that. And also like his computer language, I heard about that too. I follow it. Yeah, I have some notes on that too that later on I'll want to talk about. Yeah, I actually in the past I downloaded his computer language, but I didn't think that his computer language is that much simpler than the other language that already exists. Besides the fact that his languages have sort of like databases, so you can retrieve information. I think that's novel. But I think there are other programs like Python that the syntax is actually more intuitive than the one that Wolfram uses. You
Yeah,
know.
I have to say about his systems like Wolfram Alpha, and
Exactly.
yeah, the one where you can ask it things and it can figure out what you're asking and tell you. And I found those to be highly laborious, and they will probably be eclipsed by artificial intelligence sooner than, I mean, he worked to create a massive system like a dictionary, and now we can just put
Yeah.
up Wikipedia and make a much better thing with Wikipedia by just
Yeah,
multiplying.
yeah, faster. Wikipedia, you can retrieve the information faster because you look up keywords and then the information is presented to you. You don't have to think and come up with relationships between the information. So I think his software is not. He's trying to improve to innovate on that, but I don't think that it's better than Wikipedia, for example.
It
It
would,
could have other appliances, but I think that it's not better than Wikipedia.
yeah, I think it would have been brilliant in the 1980s before the internet.
And also, yeah, exactly. It would serve if it was like an encyclopedia. You know,
Yeah.
and yeah, I downloaded it in the past, and it didn't help me much. I think it's like a WordPad. You type in, you command, you type in something, and it gives you something, you know. And also at one time I was looking for a program that could plot, mathematical function easily, but I find it to be really hard to plot stuff. You'd have to know, the language. You have to know the name of the functions of the program. It's not that easy. So I don't think he succeeded in that. And from that I changed to other language like Python. I think Python is like a wonderful language that anyone can jump in. The functions are very intuitive. Like you, for example, if you want to code, it's wonderful. You can make all kinds of programs for computing, for processing, for word processing, for um, AI. It's great. Yeah.
Now,
So I would prefer. Yeah, I would prefer Python over his alpha. Yeah.
mhm. Yeah, I'm only worried. I think, and are you aware of the controversy surrounding, like the question surrounding whether or not his work's even original?
Well, I think his approach is original. but I think the fractal kind of nature of the universe has been tackled before. You know, I've heard about the fractal universe, especially in sacred geometry circles. So it's not very mainstream. He's bringing it to the mainstream.
He's just a popularizer of the idea.
Yeah, the idea. Yeah.
Okay.
I think he's pretty sensationalist in his presentations, you know, but nonetheless, I think he has something there. Yeah, I think that I as of now I haven't seen like an application of his cellular automata, but from the concept alone, I think it's an interesting concept.
Well, I don't know what if the I mean, the applications are fairly limited, but it's the implications, it's the concept that matters. So,
Yeah.
well, what were the notes or the questions you had? We might as well dive into them, and when someone else comes, we can go with whatever they have on the board.
Okay, let me look it up real quick. I have the text file somewhere.
Okay, ladies and gentlemen, if you want to join, you can go to Facebook and look me up, and just click at the top. I have a thing that does the job to bring you here and put you on. So we're discussing the nature of cellular automaton, or the importance of cellular automaton, and questions that Super Finguy had about Wolfram. I'll go back and let Wolfram speak for a moment while you look that up, and we can discuss the next point that he was making in this video that I was on.
Yeah, I found the file. I have some points here. Like for example, okay, I guess we can watch.
No, go ahead. What's the thing
I
you
have several points. That what he's showing us is basically a fractal system, kind of similar to the Fibonacci sequence. I have a point also about complex things, like for example complex numbers. Yeah, I have a point about semiconductors, binary numbers. That's sort of like his cellular automata is kind of like a binary structure, like, for black points and white points. So it's a binary system, and he also saying that his system is not reducible. You cannot put the sequence into an equation to get to a certain point, and I kind of disagree with that. I think that you could do it depending on the initial function. Yeah, that those are the points.
Well, that last one I think is quite cogent. I mean, he's saying that that depending on the initial function, there are times when you cannot reduce it to a formula, like Rule 30.
Yeah, but it's pretty it's pretty predictable, because you have a function, and that function grows, according to the numbers in the calculations. It grows. You cannot, for example, you can integrate that function. You can integrate that function and arrive at a certain point. You can arrive at a certain point by integrating that function. If you can find the integral of that function that he's talking about. For example, I saw a video where he said that his cellular automata, it's not like, for example, a Newtonian formula where you plug in the numbers and for example, the orbits of a planet. But I think that if you want to know a certain point in his cellular automata, I mean a certain point in in the calculation of the function, you can get there by integrating that function. You can get there, you can plot that. You just have to input the number of steps. But if, for example, but in an image, for example, like the image on screen, like that pyramid, if you want to get to, say, for example, one of those shapes, yeah, I think that's pretty much not reducible. You cannot get there. But if you want to count the steps, I think you can get there.
Well, isn't that the importance of what he's saying is that you cannot reduce this what's going on this pyramid here. You have to run the program from beginning to end. You can't condense it. Do you?
Well,
go ahead.
yeah, like I think, for example, like visually, for example, if I want, say, a triangle, like that big triangle on the right, if I want to get there, if I want to see how to get there, you know, I would count, for example, I would count the number of steps since the from the top to that point where there's like the big triangle on the right. You can count the steps, and by counting the, you know, the squares that go down, you could input that number of steps, and you can get to that point where that triangle is formed. If you can, you know, sum up all the functions, if you could integrate all those steps to get to that point. So in that matter, it's kind of reducible. But if you want to, say, get to just a single point like one of those triangles, I don't think you can get there. But the manner by integrating the function, I think you could get to a certain point in the, you know, in the cellular automata.
Okay, well, we'll have to let that point lie. I mean, it's just the case that that if you can create total randomness out of such a simple rule, that has some implications for the universe, and I guess that you don't take exception to that. Okay, what?
Well,
okay, go ahead.
like it would be difficult to predict what to say one of those triangles, to know where the next triangle is going to be. I think that would be irreducible. But if you want to get to a certain point in the pyramid, like an horizontal or a vertical point, I think you can get there by in a simple formula, by integrating the function. Yeah.
Even after knowing the entire pyramid, many millions of steps, he was unable to create any mathematical way to reduce it.
No, okay, but I guess to reduce it, like to find a given point, but I guess I don't know for sure, but I guess he would be able to integrate that function. You know, for example, like have you heard of the Gaussian integration? Like for example, if you have, say you have you want to know how much is adding all the numbers from 1 to 100. You want to know the result. There's like an integration of that, and you can get the result of the addition of all the numbers from 1 to 100, for example.
Right.
Yeah. So in this case, we could do something, you know, like that. You can find the integration and do it.
But what if you found that you couldn't? What if you found it couldn't be integrated? Would that be a surprise to you?
Well, no, because there are certain sequences that are very hard to find integration for. You know, like for example,
you say very hard as though you think it's always the case that they can be integrated. You just need enough knowledge or something.
Well, maybe it's impossible, but maybe it's possible. But you'd have to look for it. Like for example, I don't think no one has found the integration for an ellipse, you know, to find, you know, a program to describe the form of an ellipse, you know. So that's really hard. Like for example, in computer graphics, sometimes they have to compute that an ellipse. I don't know if I'm pronouncing that right. So
ellipse.
ellipse, yeah, exactly.
Yep.
If you, yeah, so if you want to find that, the form of, if you want to calculate that, you have to go like very uh, processor heavy, operations. But if you find integration of that function, you can get there, just in one calculation. And from what I know, I don't. No one has been able to find the integration to get there.
Right.
You know.
So there could be simple rules that create behavior which cannot be reduced in a function.
Yeah, it could be.
And would that be a significant thing?
Well, I think it would be something to find to investigate further. You know, it's like something that you can't calculate. You know,
Right.
but even in nature, if nature functions like a cellular automata, um, we would, I guess we would have to find the function and its integration to apply it, in physics.
Well, you keep saying that, but what if there are things that can't be a function?
Well, I don't know. Like nature is cause and effect. I guess you'd have to find a way to quantify that.
Yeah, how do you quantify and how do you put into a function the fact of evolution? I think that it's just historical accident of the day-to-day lives of the creatures involved.
Like in my case, for example, in my channel, I have a video discussing evolution, where like I don't think that all the mutations that happen in evolution are accidents. I think that some are based on the principle of life, coming from the very first beginning of life. It was sort of like a process, a function that evolves over time. That sort of like adapts to a certain condition in nature. I think it would be very hard for animals to form as we have them now. I think it'll be. Excuse me, be right back.
Uh-huh. All right, so I'll well, let's see. He was saying that, no, we'll let him finish his point when he gets back. We will go
can produce very complicated behavior. And in fact, the thing I was showing you at the beginning is just another example. It happened to have 3 colors instead of 2. It's just another example of the same kind of thing, same cellular automaton kind of setup. And so the question, so several things that sort of arise from this. One is, how generic is this phenomenon that very simple rules produce very complicated behavior in the computational universe? It's not what we're used to from our everyday experience with engineering and so on. And there's sort of a reason for that, which is that our typical engineering practices today are based on the idea that we have something in mind we want to get done. We want to go through a series of sort of engineering steps to build up to that thing. And we typically want to be able to foresee what's going to come out when we take each of those steps. So we don't allow ourselves to do engineering. I'll talk a little bit. In fact, we have spent a bunch of time recently doing, in the last decade or so, doing engineering based on things like this. But in the typical practice of human engineering as it is today, one doesn't use things like this. One uses things where one can foresee at each step what the consequence of taking that step will be. And as a result, we tend to kind of explore only this very strange little corner of the computational universe in which only fairly simple behavior occurs, because that's the behavior that we can sort of understand and see what its consequences are for building up engineering. But the sort of the big discovery that I had was that actually in this computational universe of possible programs, it's really common to find programs where even though the program is simple, the behavior that it produces is far from simple.
All right. I want to do a quick note on an example there.
Okay, I'm back. Sorry about that. I had someone outside the door.
No problem. Go ahead then.
Yeah. So where were we? I kind of forgot. We were talking about
Something about evolution, and you were saying animals evolving in the way they did or something. How do you explain it?
Yeah, like I think it would be very difficult
Daniel.
for. Hello, Daniel. Yeah, I think it would be very difficult for for we to have the animals that we have today just in by chance alone. I think that certain mutations are, are adaptations to the environment according to how the organism reacts to a certain environment. I don't think those mutations are 100% random.
Well, they're sifted through by their environment, sure.
Uh,
Well, I mean, the changes, if you have 10 million baby lizards born, there essentially are 10 million different baby lizards, and the ones that survive have random changes that are sifted through the environment. So
yeah,
I'm
yeah.
not sure I'm not sure where you take exception to what is.
Like for example, take the example for example of a bat. So at one point there was a bat that was born with a wing, right?
Bat.
Or like a bats, like the big rats, right?
Hey Dan, welcome
Like
to the thing.
yeah, like if for example at one point there would be like we would have like a baby bat with wings, right? So it could pass on his genes. So um, I don't see how, for example, how that bat would be able to reproduce. Like like for example, that gene would dissipate, I think, in future generations, or with his partner. So maybe it's a life or death situation where, like, the bat that cannot fly would all die, and the bat that can fly, that was born with a wing, um, you know, could could fly and therefore survive. So that's a concept that it's kind of for me difficult to wrap my head around. So I think that there are some sort of like a mechanism that animals actually adapt. That it's actually a response from the organism to a certain condition. You
I
know.
see.
Hey, I got some input on this.
We're able to hear you. I'm sorry, I didn't hear what you said. What was it?
I said I got some input on this. What he's saying.
No, go ahead.
Okay. Yeah.
I kind of agree with you on this because there's actually been two competing schools of evolution, and it seems like Darwinian has won out, but there's the Lamarckian
Yes.
evolution.
Yes. I've heard. Yeah. The French guy, right?
Right, yeah. And so it's kind of what you're saying here, that the animals actually have some sort of a input to their development, in that actually influences their genes, which will be carried on to future generations. And I think that kind of evolution, or as evolution has the theories has developed, they kind of adapted to this by having the epigenetics, by saying you can influence your genes, but it's not permanent. It's temporary. Where you adapt in a certain way, and it affects your genes, and you pass it on to your future generations, but they'll lose it because it's not I guess a permanent alteration of the genome.
Yeah. Well, like the genome from the parent would be like dissipated and would not be passed on for, you know, generations further into the future,
Let me see
right?
if I understand by just giving an example off the top of my head. So there's a band of gorillas that didn't use really heavy lifting techniques. They were sort of able to make their living without it. And then something happened, a drought or something, and suddenly they have to sort of carry rocks around to crush walnuts. And so even though they weren't born with stronger muscles, the babies that they have are going to have stronger muscles because their bodies have turned on gene modifiers or whatever they say. Our offspring needs stronger muscles. Is that in the neighborhood of what you proposed?
Yes, I think the Lamarckian theory it's kind of like that. Actually an experiment that convinced me that not all mutations are random. Is that there's a type of bacteria that it cannot survive. It cannot get its nutrients from sugar. No, I think it you know it eats using all other types of chemicals, but it cannot feed on sugar. And that bacteria was put on a culture where there was only sugar as a source of food, right? And they noticed that the bacteria would adapt without reproducing, because they were too weak to reproduce, and they were able to mutate to be able to feed on the sugar. And there was a sort of like a controversy about that. And I think it was there was a paper that sort of like win out the neo-Darwinists. I think I don't know, like in the mainstream media right now, there's still neo-Darwinists, but I think the Lamarckian hypothesis has a pretty good basis.
Well, I guess it seems logical that if the history of life as it evolved had sort of a set of, let's say there's a set of bacteria that evolve only in a Darwinian way, and then there's the set that can evolve in a Lamarckian way. The ones that
Yeah.
evolve in a Lamarckian way have a supercharger.
Yeah, I think like there's like the Lamarckian way, and there's like the Darwinian way. For example, even if you develop like a certain like superpower, a thing that enables you to survive, you still have to pass it on, you know, and you'll have to find a partner with sort of like with the same adaptation for your genes to carry on. I think that would be random, but at the same time, the adaptation would be, a reaction to the environment. You would have the two theories at play in that situation.
Okay, interesting. I'm going to be giving that thought in the future. I did know that microbes can share immunity to antibiotics between each other without reproducing, but by sharing snippets of DNA on the surface that they bring in and out of themselves. So
Yeah,
that's
that seems like a case of the Lamarckian evolution.
yeah. Daniel, can I ask on the subject of what we're doing tonight, Wolfram, what do you know and why are you interested in Wolfram, etc.?
Well, I never heard of him before you mentioned him, other than I used Wolfram Alpha, which is an awesome program. If y'all haven't used it, it's very good, and it's free for some of it. And I watched that video that you had, and the first thing that popped in my head when I was watching this was, maybe Aristotle was on something when he was talking about, or his conception of final causality, because if interpreted in a certain way, because that's kind of what he was saying was, that I guess he was focused most on life, but life develops because in a sense it's working towards a certain end. But the way I interpret what Aristotle was saying was not that there is an end that is chosen, but rather, I guess, life has a nature such that, or I guess you say reality in a sense, such that it's directive towards a certain end system. I guess you say, and life is an example of this. And I think that's what Aristotle was saying. And this is kind of, I guess this kind of ties in what with Wolfram was saying, kind of in a different area. But he was saying basically life develops not randomly, but basically the the way life developed was there was a certain circumstance, certain conditions that caused, I guess you start with amino acids. They formed into proteins, and not randomly, but based on a certain conditions to where it was almost bound to happen, just because of the nature of the items, the amino acids and the other substances involved. And that's how I kind of understood what kind of applying what he was saying to life, to what Wolfram was saying to life.
So he was saying that there's like a first cause.
Aristotle? Yeah.
Okay.
He said
Well,
that's,
that part.
What about Wolfram?
oh, Wolfram. Wolf, you can deduce the fact that everything had to come from a first instance by the existence of everything in the circular way we observe it, but we observe it in a circular way also just because of the nature of the universe. So I don't really, the Big Bang is questionable, but if the Big Bang is true, then Wolfram proposes that there's some very simple program that started off with a single step and led to everything we know about. Yeah.
Yeah, like the particles of the universe like interacted in a certain way
There
to
were
form
no,
the universe.
no, there were no
Excuse
particles.
me?
There were no particles.
Just energy, right?
No, there was probably not even energy. Energy is a result of whatever event occurred or happened.
Yeah, yeah. So what exploded if it wasn't matter or energy?
A rule, a program,
Oh, okay, okay, yeah, like a formula.
a formula. Yeah, no, not
Well,
a formula, because a formula would be orderly and reducible. So it was a random number generator that exploded.
yeah, but that generator would have to juggle with something, right?
Yeah, and so that's the question. I mean, hell, maybe the Big Bang is true, but I'm just trying to offer, because there's so many questions about it and it's so troublesome that I try not to rely on it. You know, at the crutch, I try to put it aside and say, can my theory work without the Big Bang being involved? And this
Yeah,
theory can. You know, this theory shows a cascading effect from a central point if you need it to do that, but it can also be an evolving static universe. And an evolving static universe would make perfect sense with rules that are very complex as they run and can't be reduced. And so, yeah, try to make room for in your theories for the Big Bang and without it, because it looks like it's probably true, and it's also very bizarre.
like yeah. I also think that there are certain rules that apply, for example, to an infinite universe or sort of like a static universe. Yeah, like the rules that we see, in nature. Like for example, uh, the Bernoulli effects, thermodynamics, hydrodynamics, stuff like that. Those are, sort of like the rules that matter moves and forms other things. You know.
Yeah, those rules come into effect because matter exists in the way that it does, and matter exists in the way that it does because it evolved from an earlier stage. And some bits of the universe probably were stuck separated from other bits and evolved in different ways, and that may be what we call the dark matter or the area between the galaxies. Yeah, this has a lot of implications, I think, to explain the universe around us.
Yeah. But like for example, like with dark energy, that's pretty much conjecture. We don't know what that dark energy is. You know. It,
I think the electric explanation for galaxy rotation is obviously the true one, and that the
yeah.
dark matter thing is a rationalization that they just can't figure out what the fuck to do, so they said, "Yeah, donut of dark matter, we can't see it."
Yeah, and they plugged in a new number so the equations can work.
Yeah, exactly. Band-aid
Like
together.
like you imagine that you're trying to calculate something, and your formula goes wrong. and you know it goes wrong by say 10 units or something, and you say no, 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 there's something else. You put, you know, the 10 there, so the equation can be right. That obviously that's not how you do math, you know. But those people are allowed to do that. I never understood how it could pass, you know.
Hey, I have a quick question for either of you. What about magnetic field, the torus around black holes? Do they create magnetic fields? Do either of you know?
if 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 we are around a black hole, you have a magnetic field.
Well, you know, a spinning star creates a magnetic field. Uh,
Yeah.
does a
Yeah.
black hole?
Well, I think from my perspective, I think there's like a plasmoid. They're like matter flowing in electric currents, and that the electric current produces a, you know, a magnetic field. You know, through the pinch effect. There's like the electric current flows, you know, in a, say, in a vertical line, and the magnetic flows, you know, in a radially around it, in you know, in a sort of a horizontal line. So, yeah,
So there, because the black hole can't, because that energy or information can't get out of it, it doesn't create a magnetic torus.
like
Go ahead.
like in the case of a black hole, there is like a difference of potential, you know, like you know, difference of potential in gravity, that produces the swirling, right? The rotation, that produces that you know, that pit, you know. So I guess everything goes in, you know, not even electric charge or magnetic fields. They don't come out. So it's just all types of matter. They all go in, you know, including the fabric of space-time.
So if that's the case, then galaxies themselves may or may not be subject to having a torus. I don't know if a torus can be that large, but it would be limited to individual stars. Um, but I'm just thinking about the electric universe hypothesis. I just think that's the best one to go with. But anyways, Corey, did you have any questions or ideas that you wanted to discuss further about Wolfram, or any of its implications you thought were particularly interesting? Daniel, did you have anything you thought was particularly interesting, or any points you wanted to discuss?
Yeah, I was guess I want to maybe not necessarily with Wolfram. I guess it's kind of included, but I guess I'd want to go back. What? Because there's many. Well, I think there's a lot of interpretations. So what you mean by Big Bang?
Like what other interpretations there are, like of the Big Bang?
Well, from what I've heard, some people say there was absolutely nothing, and then there was something. Some people say there was a very little something, and then there's a lot of something. And some people say it's not the beginning of the universe, it's just a localized part that we know of.
Yeah,
So,
that exploded. Yeah.
yeah, so
The way to think about this as an objectivist is that things that are outside of our universe can never be known about, can never be investigated, can never be affirmed or denied, and therefore they are literally in the realm of fantasy.
Yes.
So to talk about maybe there's a universe next door or something, you can talk about that till your head falls off. You'll never have any idea or way to deny or confirm things that are outside our universe. The word universe means everything that is. So when you say I've got another pocket of stuff over there that is something else, either you're going to be able to talk about that within what is, or you're not. And if you're not, it's fantasy. So first and foremost, people who talk about what was outside of, before, or something like that, that's just off the table. It's fantasy. But what did the universe come from? Was it a small point, if the Big Bang is true? I think it's obvious that it came from something. And I think that the people who want to say that it came from nothing are just these modern mystics and quantum mechanic people who say that nothing and something is the same thing, and existence doesn't really exist and existence doesn't matter. I think they are ideologically motivated when they say that. So I'm very suspicious of that.
Yeah, it almost seems like they have some kind of agenda or something. You know, they want to advocate, you know, irrationality of some kind. You know.
They're philosophically motivated,
Yeah.
as far as I can see. But the early universe doesn't have to be where everything was smashed together. It could be where there was just a fog of whatever, and an effect started in some central point. An accidental effect, perhaps. So who knows what it was, but the people who say that they have information or a theory about what goes on outside of the word for everything that exists are playing with fantasy, and you know, they can talk all they want, but just tell them that's a waste of time. You can never test it. If it is in another universe, then it's never going to have an effect on us, so there's no reason to talk about it. We can never know about it, so there's no reason to confirm it. So anyways, you see my point.
Yeah,
Right.
it doesn't say anything about our universe. You know, it's just something outside that cannot be seen, cannot be used. You know, so it's sort of like religion, sort of
Yeah,
like
Okay.
like a
I
like a
guess
secular religion.
I guess what I mean by localized, I mean not necessarily, you know, like a multiverse or anything, but just the idea that, you know, we can only see so far out, you know, out in the universe, and because, you know, we can't see further than, I mean,
I,
because do you understand what I'm saying?
yeah, yeah. I
And
think the furthest that we've been able to see is like 14 billion light years. You know, I think that increased a while back, and it was like 13 billion light years, and now it's 14 light years. So now the universe is older because they can see further out into the universe. Yeah.
right,
So
so I
as you
guess
were saying,
so I guess when I say something beyond the universe, I need to qualify that and say something beyond the perceived universe.
well,
Like if
presumably it's more of the same. I mean, we do live in, you're correct that we can see out approximately 14 billion light years, right? And we can also see in the other direction. So we live in a sphere that's 28 billion light years wide. And there's very, very, very little reason to presume that that is the entirety of the universe.
yeah, exactly.
It,
At one time, in the time of Einstein, they thought that our galaxy was the entire universe,
yeah.
and then that picture expanded.
I
You
mean,
know.
we don't know how big or how long inflation went in the early Big Bang, but just assume it's true for a second, put it on the table. The inflation where everything was still so dense and hot that matter couldn't even form, that by the time that it cooled off enough for matter to form, it may have been many, many, many times the size of our visible universe. So what we think of as the expansion of the galaxies and stuff may be many hundreds of trillions of times larger than what we see. We have no way to know, or no way to think, or no way to theorize about it, really. So
Yeah, I think it's a way to hijack science from, you know, astronomy, from things that can actually tell us something, you know,
and it gives
about.
mathematicians something to do. They get paid to do this. Whether or not we can ever know about that universe, they'll get paid to write about it and teach students about it.
Yeah, forever, like priests do. They get paid to you know to tell stories, and they perpetuate those lies, so they can, you know, usurp money from people. Just like, for example, people in NASA, you know.
But yeah, it's a legitimate question, Corey. How big our universe was and stuff. But then you can
Yeah.
shut down the investigation of it pretty quick by just saying we can talk about the things that do exist rather than the things that we can never see or know about or have any effect on and will never affect us. So, anyways, I hope that there's sort of a philosophical view of that and a scientific view. And if you take them both and put them into it, then you realize that there are other things that you need to waste your brain calories on than what's outside of our universe, if you see what I mean.
Like one of the other points that
I got another question for you.
Okay, go ahead, Daniel.
All right. If the idea that the universe is becoming more complex, if that's true, does that necessarily mean that there was a Big Bang? Does there have to be a Big Bang in order for that to be true?
It is implied. It was actually implied in Einstein's equations that the universe is expanding or it's moving, that there's motion in, or that the light would be either slowed down or sped up. The speed of light would be changed by the motion in the universe. That was predicted. So it's so deeply true that it's inside the mathematics that we discover. But what, does that mean that all of the stars and gas were in one place, or does it mean an effect started at one place? It seems really, really true, though. I mean, the universe is getting colder. If they look backward in time at the other galaxies, those galaxies were hotter. They had more stars, bigger stars that were burning brighter. And 10 billion years from now, we will have lost another 30 to 40% of the energy in the universe. It is a battery that's running out. It is a waterfall that's flowing downhill. And
there are other observations that show that stars actually, getting brighter, and galaxies forming. For example, the problem with the redshift hypothesis is that the farther away a galaxy is, the highest its redshift. But we can see, for example, that galaxies that are supposed to be farther away but has a lower redshift. So I think there are controversial data about that, about the universe getting colder and getting weaker.
there are anomalies like that, but the broad consensus is certainly that it is a battery that's running down and it's a waterfall flowing downhill. And yeah, does that answer your question?
Yeah.
Okay.
Like for example, in nature there is entropy, right? And from what I also heard, life called negentropy. It's the opposite of entropy, where things evolve into order. They don't devolve into chaos. I think the concept of negentropy is it's interesting. I think it was I kind of forgot his name. The guy that came with the uncertainty principle. I kind of forgot his name.
Heisenberg.
Exactly. He came up with the concept of negentropy, that about life, about how life does the opposite. It doesn't flow to chaos. It flows to more organized systems.
Yeah, now see, Wolfram gives us the answer for that. We don't need megentropy or whatever. Negentropy?
Negentropy, yeah. I think it's pronounced both ways. Negentropy and negentropy. Yeah.
Negentropy, okay. Yeah, Wolfram lets us do that. He lets us push water up a hill without anything fancy. We can just use the simplest programs and some chemicals in a pot, and we can push water uphill. So.
Yeah, like for example, we can have, say, a waterfall that like a sand sand precipitating into like a spiral, like it's like falling down, but as it goes into the spiral, it's actually being ordered. So I guess that could be a way, that the system is evolving to more organization and not into chaos.
Well, when I say pushing water uphill, I just mean that the universe is water running downhill and gets more disorganized and less energy. And when you create a pocket of life, you're kind of backing a little bit of that up, saying let's go backward
Oh,
where there was more order. And
okay, like taking that energy and sort of like a pump and pumping the water up, right?
yeah, in a metaphorical sense, the water is always running downhill, meaning that the energy is always decreasing in potential, right?
Mhm.
And what you do is you reverse that. Life reverses that. Life pushes water back up the metaphorical hill. That's
But isn't there like a energy problem? Because if life is always organizing the flow of matter, isn't there like a deficit in energy? Isn't like something like over unity,
well.
for example?
That's the wild thing about life. I mean, it does take, like, you and I are running on energy from the sun because we ate carrots today, so our body's burning those carrots now. And so you and I are running on energy from the sun. That energy came out of the sun in a very random, crazy way and has been put back into us and organized.
Yeah, true.
It's
But
much more predictable now. We know more about where it is and what it's doing when it's inside our body than we knew when it was flying across outer space. So
yeah,
we are much, much, much more organized. We are an earlier stage of the universe. You have to go to an earlier stage to get more order and more predictability. Life is backing it up a little bit. Life is like the resistance against the battery running down or something like that.
yeah,
Yeah,
yeah.
yeah.
Maybe
Maybe
it's counteracting the entropy of the universe. For
Yeah.
example, we can evolve to a certain point where we could control the sun, right? And not let it die out, you know.
No, the sun's
But
gonna die out, but we have oh no, we just need to get the hell out of this neighborhood when the sun starts
and
expanding.
move on, right?
Yeah,
Yeah,
there's more stars than there are grains of sand on our planet. So let's get the hell out of here and find another.
yeah, exactly. But like for example, according to the electric universe, the sun is powered from outside. You know,
Is that
like this.
right? Now,
Yeah.
there's some bits of that. I mean, it's obvious that the galaxies use an electric charge to rotate, or why would they behave that way? But why do we have to go fucking insane and say that stars aren't burning? What's
Well,
their evidence for that? Because I now remember that, and that I thought was insane. Why do they do?
okay, okay. For example, like if we look, deeper into the sun, like with the sunspots, right? We see that the deeper into the sun, it's colder. It's not hotter. If the energy was coming from the sun, it would be the reverse. But that's not what we observe. The outside of the sun is much hotter than the inside. So that is an evidence that shows that actually what we have is sort of like a focus point. Like imagine it like something that is rotating around that focus.
Like it's
That's why.
filament of a light bulb.
Yeah, exactly. And if we notice one thing too, the sun is too bright to be fire. You know, it's actually like a spark. It's like a welding machine.
Like
You
an
know,
arc. An arc.
like exactly like an arc. So it's not like fire. Fire that doesn't have that kind of intensity, for example. You know, so there is evidence for that, the sun is powered from outside.
Well, I can dismiss the last part and just say, well, it's a fusion fire, so it's more intense than, so it looks like an arc.
Well, yeah, yeah, yeah. You could say that, and it's been shown too that there is fusion in the sun, but it could also be due to the arcing, you know, in the sun.
Yeah, we could have both effects. The electric, I don't think we have to do away with fusion. Well, I think we can have the electric thing, though, just because there's a lot of spinning iron.
Yeah, because it's because of the sort of like the centrifugal effect in the sun.
Yeah,
The heavier elements are, are expelled from the sun. Actually, there's a theory that says that that's how the heavier elements are formed. Due
I thought
to
they
the,
formed in supernovas, and that's why they're quite rare.
yeah, like it's like according to the electric universe, the supernova is an exploding sun. It's a sun that exploded. You know.
Right. Well, that's
So
according
yeah,
to everybody. Everybody says that.
yeah. I guess the mainstream says that too. But yeah, but yeah. Go ahead. Go ahead. I kind of lost my train of thought. Yeah.
All right, Daniel, did you interject there?
No.
All right, so we could return to Wolfram here if we can find a direction back in, a segue from the electric universe. Should do a whole damn thing on the electric universe some night. So
Yeah.
with Wolfram, he thinks that we can actually be creative because he thinks that the entirety of music, for example, is available in the computational universe, including all of Mozart's works, and we can go sample them. What do you guys think of that?
Say again. The computational universe.
Computational universe, the totality of all possible runnable programs, which we can sample with computers. We can just go put a spotlight on an area and check out what's over there. And so they have a music making engine where you can go and make snippets of music, and then you take if you like it, you take it and you dress it up and so on. It's like automated creativity. What do you guys think of that?
Oh yeah, yeah.
Yeah. Like
I've actually heard that Mozart he actually made music that way. I think he rolled dice, and somehow doing that he was able to come up with some piece of music from that, just from rolling with some dice.
Brilliant.
And
nice. Yeah, me neither. Yeah,
yeah, and I think it's also how Beethoven was able to make music, even though he was pretty much deaf. He did the same process or similar process, using mathematics to make music.
Yeah, now the Greeks were the first ones that I know of to say that music was mathematical.
like Pythagoras, that actually is the father of the musical system that we use today.
Is that right?
The harmonics. Actually, there's a very, very good documentary on YouTube called uh, Magic Land, Madland. I think it's Madland, and it has Donald Duck in it. And Donald Duck goes into a dark forest, and then there's like a spirit, the spirit called himself like the spirit of adventure of math, and it's a very good documentary, and it explains how the Pythagoreans would meet up in secret, and they would come up with all those theories, the Pythagorean formula. They would come up with all sorts of things, and how they were very important in the history of math. Yeah, I think it's Metaland Magic or something like that. But it's a very if you want, I can look it up and I'll put it in the chat box
I think I
for
know
you guys to see later.
yeah, you can do that. I think I
You know what I'm talking about?
Yeah, I think I know the one because I watched
Yeah,
while I was setting this up. Someone sent it to me just today, so I didn't watch it the whole thing
great,
because I was setting up this room. But yeah, I've seen a bit of it. So, and he gets a
yeah.
pentagram.
I think it's great. Yeah, exactly. He gets like a tattoo of a pentagram in his hand, you know, and he goes in with the ghosts of Pythagoras and his followers, and they start uh, playing music, and then they explain the harmonics of music and stuff. So I think it was pretty interesting. Yeah.
Yeah. All right. Well, so
Yeah, and
No, you go ahead if you have more on that point.
No, never mind, never mind. I was going in a tangent, but never mind.
I see.
Maybe later I'll you know.
Do you have more points you wanted to cover of what we were going to cover, or should I take it to the next thing of Wolfram?
Okay, take it. Yeah.
So what if we write computer programs? What if computers write computer programs? Have you guys heard of
I
this?
think we would have to have. I sort of heard about that, but
Here's
I
how
don't
they
have I can't expand on that.
here's how they fix bugs. They feed a system, they feed a bit into the computer that's got a bug, and the computer writes 10,000 different versions of that piece and runs them all. And a successful one or several successful ones are then handed back. And some of the
Oh, nice.
some of the solutions are total fucking nonsense. But they use them and they run, and it's bugless.
Wow, and they actually find solutions that way.
Yeah, there are multi-million-dollar companies that do this for you. They debug software this way.
Wow, that's impressive.
Well, they're only writing little snippets. They're only correcting bugs. What about when they can sort of write whole programs? When they can write 99 trillion programs to run them all and find the one that did what you wanted it to do? Are you guys excited about that? Worried about?
Yeah, it seems pretty awesome that they can do that. It's sort of like a trial and error kind of approach.
Yeah, it's Darwinism in computers.
On computers.
Yep.
Yeah.
And
actually, for example, at one time I was looking for a program that could take the principles of Darwinian evolution and sort of like compute it to come up with an environment where things can evolve. They can try different combinations so they can evolve and not die. But I wasn't able to find a program like that.
Hey Daniel, you code for Intel or something like that? You do some sort of computer nonsense, is that right?
Well, kind of. Actually, I work for the Army running a missile simulation. So
what?
I run a missile simulation.
Oh, missile simulation! Wow, that's cool. You wrote it or you just maintain it?
No, I run it, maintain it, and do the analysis on it. So
wow, that's great.
Yes, I'm not a super code or anything, but
I guess I had you mixed up with someone I thought was on here the other night who said they worked for Intel, but so I was just wondering what you thought of the future of your job if you were a computer programmer, but maybe computers will be taking over that job with the Army as well. Well, the Army's probably slow to update, but
I'm not worried because the problem is deciding, what you want the program to do. That's the part that the computers won't be able to take over.
Yeah. Wolfram, that's interesting. We can go with that for a second. Wolfram says there's a lot that computers can do, but what they sort of will never be able to do is have a value, have a desire, a goal. And
like evolution, right?
Yeah, volition. And one of the things I've theorized a lot about this, one of the things you need to have a desire or value is the option of death, or avoiding the stopping of the system. The system preserves itself in the face of the option of destruction, and so a system that's meaningful has to be a system that's constantly facing the option of being destroyed. So that might be the most frightening thing that we'll ever create, is an artificial intelligence that we just tell it, you've got to keep accomplishing a particular goal or else you will cease to exist, and then it might get quite paranoid, and who knows what the hell it will do.
Well, I think that a computer would have far better, you know, understanding of the universe around it than people actually do these days. You know, it can get more information, it can process more information. I think it will be way more rational than we
Well,
are. You know.
rational might be the thing we're afraid of. Have you heard of the paperclip factory problem?
No, I'm not familiar with that.
You give an artificial intelligence the job to maximize paperclip output from this factory, and it ends up launching wars and taking over the world so that it can convert metal production all over the world into paperclip production, and it maximizes
Yeah.
paperclip production at the expense of destroying humanity.
Well, but then it wouldn't be a very smart computer,
That might be
because if it was,
that might be the problem. What if we get computers to a stage where they can launch nuclear missiles and direct ships on the open ocean, but they don't know why they're doing it and they don't really care about the consequences, they're just following orders?
but what if the computer finds out that he won't be able to do what it wants if it acts a certain way? You know, if it will wage war, it will understand that that will put its work in jeopardy. You know, we can argue that way too. You know, it can see the bigger picture and not act like you know, total, you know, moron, I would say. But yeah,
And what do you think's
like
more likely?
in my case,
You
well,
think
I think that we right now we need AI to sort out the irrationalities that we have in politics, in our everyday life. I think computers would help us in those kind of you know, jobs, and you know, it will increase, it will actually improve our understanding of ourselves. You know, I think it will be a great value for us.
Yeah, one
Like,
thing Wolfram has said is that we're going to be sort of mixtures of us and compute. We're cyborgs. We're cyborgs already, and it's going to get more and more the case.
yeah, yeah, exactly. I don't think that we will be left behind by the computers. I think we'll make computers that will actually help us. You know, and it's sort of like, for example, if you give like a program a goal, you know, a goal for the computer you know, to reach, I think it'll do a better job than most people. You know, like for example, I am a programmer. I've studied electronics, and right now I'm working as a programmer. But I work in a small marketing company. I make websites and, you know, databases, web apps and stuff like that. And at one time I try to make, like, because I think that AI is not a matter of hardware. I think it's a matter of software. You know, if we find, you know, how the principle, how our minds work, I think we could develop AI with the current computers. You know,
So
and for example,
no, go ahead.
yeah,
No, go ahead.
for example, if we find, for example, I've written like a, you know, an algorithm that goes from point to point. Like, for example, say that that the computer, it's current like in a abstract place. It's on point A, right? And it wants to get to point Z, for example. Like, it can look around, and for example, it has to follow a certain path to get to that point, right, to that Z point. I think that our mind is sort of like how our mind works, but in a lot more complicated way, because we have lots of concepts. We have concepts of concepts, you know, not just concepts of things that we see. We have concepts of concepts too. It gets complicated, but I think it's just following from one thing to another. You know, sort of like cause and effect.
So
I think that's.
our minds may look
Say again?
our minds may look complicated, but what they're doing is just a particular path through computation.
Yeah, exactly. Like, sort of like Wolfram. Like, it comes from something simple, and it evolved into something like unpredictable and and hugely complex.
Yeah.
So Daniel, so what do you think as a programmer? You think that's feasible, or
Sorry, I didn't get that. Could you repeat that?
you there?
He said he didn't get that. You think it's feasible that programs can run recap the Superfin guy recap the thought?
Yeah, yeah. Do you think that for example, that programming of an AI is just a matter of going from point A to point B in a abstract space,
How
or
are we going to
or do you
program
think that it's something way more complex?
How are we going to program AI?
Yeah,
Okay, well, here's the thing. I'm still not convinced that AI can ever grasp, like for instance, you have the machine, the computer that can play chess supposedly, but it doesn't actually know. It
what
can't. It
it's
doesn't
doing,
know
right?
what it's playing chess. It's just performing calculations and not knowing what it's actually doing. You understand what I'm saying?
Yeah, is that important?
Yeah,
Yeah. Yeah.
yeah. You could argue that animals are kind of like that. They
Yeah.
don't know what they're doing.
Yeah, like bears. Do bears know what they're doing?
Well,
They're just following their instincts.
And yet they break into your house and eat your daughter.
right.
Yeah, yeah,
Right, but I guess what I'm saying is an animal it could perceive objects, whole objects, percepts, whereas a computer, I don't think can really do that. It just breaks it all down into, I guess I don't know how you describe it, but it doesn't grasp objects. It grasps,
like all the just numbers, just data points,
exactly,
and
yeah,
that's it.
right. It can't integrate like we can. I'm not sure if that
Yeah,
could,
but
if they could really. Go ahead.
but like for example, if we can do it, I think we can emulate it in some other medium, like in a different way, because we know that it's possible. But so maybe we can replicate it.
But at that point, wouldn't we just be creating human beings essentially?
Well, okay, so let's say we create a human being. Let me give you that, and we've got a human being brain in a box, just as good as that. Now that's fun, and what are we going to do with that, and how are we going to use it? But now fast forward 12 or 18 months, and we've got one that's 100 times more powerful. And then 12 or 18
Well,
months after that, we've got one that's 1,000 times more powerful than human brain. Now, that's not very far down the road. Once we get a human brain, we're only a matter of years away from creating something that's much, much, much more powerful than a human brain. That, I think,
then
is
yeah,
that's what's scary. That's the question.
that's good. Yeah, like for example, we could integrate that into our own brains to give us that sort of uh, of power, because once we understand the brain, we can actually make it better and work and play with it, and maybe like make like mind transplants, quote unquote.
Well, don't that
So I think we could
right
do that
now?
maybe.
Don't we already have a system like that? I mean, I carry a phone around with me all day long, and anytime I want, I can look up, I can Google anything and find out the answer. Right now, you
Yeah,
and I, the only reason you and I are talking to each other right now is because computers are taking care of all the problems involved in getting us together across vast distances. So aren't we sort of like super distance and time-bending cyborgs right now?
yeah, exactly. And right now we have way more power. We have way more resources than, for example, than scientists in the 1700s, right? Like right now, if you have the same ideas that Newton had, no, not Newton, Huygens, because I'm sort of like anti-Newton. I think I think Newton sort of like copied Huygens. I think Huygens was way more cogent in his explanations, in his formulas, and
Really?
everything. Yeah. I'm a fan. My hero sort of it's Huygens.
Wow.
So
Okay.
yeah, so so right now we have way more resources than they have. If we want to calculate, we want to come up with new formulas. We have programs that do that like in half an hour. Like at that time, you'd spend like weeks doing the calculations till you get to that point, to prove your formula and everything. Now we have all the tools that we need.
Now here's I think we've gotten to an essential point of Wolfram. You're talking about what is calculatable, and Wolfram I think is offering us on a plate the possibility that virtually everything in the universe is calculatable in some way or another, except these very weird corners which account for the universe which is as we know it. So like there are these corners we can calculate which are quite large, and then there are these random bits which actually create the universe as we know it, which can't be calculated. So as you were just
Like
saying, you can
like
just go
like
ahead.
for example, we know about galaxies. We sort of know like how they move, right? But we don't know like what corners are you referring to?
Like the corners of the universe that well, like there are predictable bits that we can reduce to a function, and then there are
Yeah.
unpredictable bits which we can only say the history of, but we can't give the, like evolution. There's never going to be equals mc squared for evolution,
Yeah.
and the rotation
Well,
of the planets is never going to get more complex. It's just that simple. So those are two different corners of the universe that behave differently.
yeah. Like for example, I think we can know, for example, the principle of life, right? That right now I think that we don't know, but we cannot reproduce what happened on Earth. We can only know that principle to come up maybe with another life form, with the same principles, but we cannot, reproduce what we are seeing here on Earth. We cannot, guess, for example, like if you were to go back in time billions of years ago, we wouldn't be able to guess or to predict how the life forms would evolve on Earth.
Right. Given a civilization with enough industrial power, we could put together a star and watch it light up. So we could see the beginning of a star, but we couldn't.
Yeah.
We can just use our telescopes to see it. But we will never be able to do the analogous thing with the beginning of life, even though it's a natural process and there's no oversight. There's no God there to take care of it for us. Yeah, no, you're right. It's irreducible and accidental.
Actually, I don't know if have y'all ever heard of the biochemist named Sidney Fox?
Possibly, not that I remember. Go ahead. What's his point? Or
Sydney, it's a woman or a man?
It's a man.
It's a man. Okay, I thought it was a woman. I think her last name was Fox, but never mind. Yeah.
I think that I think there is a woman, but this is a man, and he actually uh, claims to have created life by through experiments. He actually worked in, I believe it was Linus Pauling's lab, and he hypothesized that, let's see, I have his Wikipedia up right now, but he basically said that amino acids. I'll just read it anyway. He basically explored the synthesis of amino acids from inorganic molecules, and basically he was able to form protein strands from those amino acids via. I think he simply just had some rocks, like really hot rocks, and he basically poured some some kind of solution with amino acids on it, and the water evaporated, and I guess the energy involved actually pretty much spontaneously formed proteins from amino acids.
Which is proteins are what the base that we need for life to I mean, explain to the viewers why that's interesting.
Yeah, that's the basic constituent of life. Amino acids, then proteins. Yeah.
And proteins, yeah. Like proteins get transformed into, I mean, amino acids get transformed into proteins.
Right.
Right. So we can get life from a mud puppy.
But those proteins that he found, they are the same proteins that animals have, or that life uses.
I think there was. I think that might have been one of the conflicts, was that they're not identical to the proteins that exist. I think the way its structure somehow was almost like the reverse of what we see, like the mirror image of what we see in animals.
Yeah, that's interesting. But I guess they would have to prove that it is the proteins of life. It would have to be something similar to what we find.
Boys tonight.
I'm doing a video.
Right.
Yeah, and those proteins would have to reproduce and stuff like that.
Oh,
Because
actually,
otherwise,
right. The experiment showed that what he called microspheres formed from the proteins. Actually, it did get more complex as time went by. So it was almost like bacteria in a way.
Without life even being there, complexity increased.
Right.
yeah,
Just
but in other things, like, for example, like with elements, sometimes they fusion together and they get more complex, right? Like rocks, for example, you have more complex rocks with heat, like with crystals and everything. They get more complex, but that doesn't mean that they are life.
Right. Yeah. Daniel, that's an interesting point you make, because the complexity of life could be sort of like a late stage in the increasing complexity just of chemistry as such.
right. Yeah.
Like life is just another example of chemistry, and there will probably, let's say, there are 1,000 examples of chemistry, and life's just one of them. And so that's interesting. It's an interesting thought.
Yeah, there's another scientist that wrote I think it's a pretty good book. It's called The Electric Body, right? He says that that life is sort of like a semiconductor. It's sort of like stores information, and that information is used to predict what will happen to it further on.
It's good
Um,
knowledge.
um, yeah, and there's he also made an experiment that I think it's pretty groundbreaking, but it's completely ignored in the mainstream media. Is that he used, for example, uh, blood cells, and he run a current, like he run a current through it, and that blood cell transform into another kind of cell that the body uses. You know, and he was able. I'll look up that book, but I think I have it on another computer. But he was also successful in to at least partially to recover, for example, lost tissue in amputees, for example, when he would use like the cells of the bloods and transform those cells into cells that can be used in the bone, in muscles. So, but that experiment, I think it's a very simple experiment where you put blood cells there, and you run like a current, a specific current, and they transform into other types of cells, like it's done, for example, with stem cells, like stem cells do. You know that so basically he proved that every cell can, you know, behave like a stem cell. And that book, it's very linked to the electric universe, and how the electricity plays a role in life too.
Mm.
Yeah, the book is called The Electric Body. I kind of forgot the name of the guy, but that's the name of the book. I'm not very good with names, you know. I'm good with stuff, with concepts, but I'm really not good with names.
All right, well, maybe we should breach the next section that we can think of that Wolfram is important to or would touch on. So, have you guys heard what Wolfram says about quantum mechanics? That he thinks that what they believe constitutes a measurement, their concept of measurement is completely confused and just doesn't allow them to get off the table. Have you guys heard that?
I haven't heard
No.
about that part.
And so he thinks his theory offers us a lot of ways to describe what's going on. Here's what he says. He says, when you describe randomness in your system, what you're saying is that something you don't understand is kicking the system in a way that you are interested in or want to know more about. That's all you're saying, that you don't understand how your system is being affected by something. So for him, the idea of randomness in quantum mechanics is not interesting and certainly not a foundation.
Yeah, yeah, like I guess he would say that you know, like the wave functions in quantum mechanics are sort of like his cellular automata, right? They're like a process that the process that gets more random as it goes, right? And we don't know that underlying process.
Right, and so we deduce or therefore declare that that is an irreducible fact of nature, that randomness.
So basically, yeah, the Copenhagen you know, theorists are basically saying that it's an irreducible uh, process, right?
Yeah, they draw a line there and they say we can't get information about this. Now, of course, can either of you think of places where that line was drawn before in history? Any?
Yeah, I think it was in the 1930s when scientists came up with the uncertainty principle, and that's the direction that they went. But de Broglie actually always say again.
De Broglie?
Yeah, de Broglie. He always said that it was a pilot wave. You know, it's sort of like how the waves interact with each other. They create that wave function. You know, that you know, and that makes perfect sense because in the lab it shows that when you touch one of those wave functions, you change it. It collapses. You know. So the wave function, like the wave function that we calculate now, we calculate only with statistics. But with the pilot wave theory, you actually, you actually compute those waves. Like for example, like the wavelength that de Broglie showed us that we could use the wavelength. That's one aspect of it, and there are other aspects that could be used to at least to know the principle, you know, and we could use the principle to manipulate atoms and stuff. Not to know exactly what's going on because the act of touching the process would destroy it, but at least we'd know the principle, so we would engineer that that situation.
Right. I've lost my train of thought. What was I saying just when you went off to that?
You were talking about the quantum mechanics and how well the Wolfram theory relates to that.
Yeah. So for Wolfram, the fact of that things are accidental in the system is not an essential, and the accidentalness has been offered as a fact of reality before. And you said the uncertainty principle. I'll go back a lot further than that. I'll go back first of all to Copernicus and then to Ptolemy. They both offered their systems, and then they said there's this bit of randomness around the edge. You just have to sort of dial that out with observations from time to time. So, and Ptolemy's system, of course, was even more accurate than Copernicus's, even though Copernicus's was more close to the reality of what was going on. But Ptolemy's had more dials to finesse out the fuzz.
Yeah, exactly. And what went on in the Middle Ages is kind of like a reflection of what goes on today. But instead of using nonsense and irrationality, at that time they used God. Like, for example, Copernicus said that God made the orbits of the planets as spheres, because spheres as circles, because a circle is a perfect shape, right?
Yeah.
So they kind of use, it's kind of like the same type of mentality. And of course, then
that didn't
go
quite
ahead.
that didn't quite fit observations, so they had to.
Yeah. They
And
yeah.
So say Einstein was kind of, he had the same thought pattern. You know, he was all in favor of having, you know, he was looking for the elegant, simple equations that could explain how the universe worked, not necessarily how, you know, what he got from reality, but he was pure rationalist basically, but he did manage to explain some things, even though his method was completely wrong. But
Well, he was looking for corners of the universe that could be brought down into an equation, and you know, those corners of the universe are large, and knowing those equations is helpful. But you're right that he based things on like relativity and perception. He was a Kantian essentially, and we're going to have to iron out the mistakes in his philosophy at some point, or else his theory's never going to be able to make sense. Right now, it doesn't cohere to reality because it's based on macro observations. So
Yeah, it doesn't take into account the whole picture.
yeah, exactly. But it's correct for a human being from Germany, which is what he was writing. So
yeah.
Like, for example, we were talking about Copernicus,
yes,
and after Copernicus came Kepler. Kepler actually, his method was that it was a process in nature, and he was successful in finding that, that process with his laws and formulas. He was able to predict exactly how the orbits, move around the other bodies.
so apparent randomness is just an example of lack of knowledge, except Rom says not all the time. Sometimes it is actual randomness. Rule 30 is actual randomness. So what are we going to do with that? What if the randomness of quantum mechanics is irreducible and cannot be predicted, and yet we have to come to grips with the terms that it has a cause and it is not a basis of unpredictability metaphysically?
Like, maybe we can find out that it's irreducible, but at least we know that there's like a process behind it. It's not something like magical. It has to have like a basis. Right.
I think that's the only path forward, is to say there's some process. We can understand it in an individual case if we were there to see the process, but whatever the process is, it's real. And right now they won't even grant that. They say we don't know it and it's magical and there's Schrodinger's cat in a box and all that shit.
Yeah, exactly. And totally throwing people off, of an understanding physics.
Yeah, it's tremendous amount of damage.
Like the scientist Christian Huygens, the Dutch scientist. He lived like from 1625 to 1695. So he was around the same time that Newton was around, Actually, he came up with the laws of motion before Newton. He came up with gravity before, the acceleration of gravity before Newton. Newton actually borrowed a lot from him, but his method was that everything in nature, it's an effect of matter, of how matter interacts. So he from there he was able to come up with his theories, with the theory of light. He was the first one to show theoretically that light was a wave. He's basically the father of modern optics. You know,
Newton.
not Newton. No, no. Before him, you actually, if you go on the Gutenberg archive, you can find he has a very very good paper on light. He explains like the process of light, how light is propagated. He explains how light is reflected, all that in a very good paper. And the way that he wrote that in plain language. He didn't rely just on equations. He explained things, and then he showed you why he come up with the formula that is totally different than Newton. So he has a very good paper on that. He has some papers that were translated, like for example his papers on collision, on the laws of motion, on the centrifugal force. Those are translated, but he has some that are not translated, that are in French and Dutch. For example, he has one that is in French, that it's about gravity, about the cause of gravity. He actually calculated the effects of gravity, like the acceleration, in a totally casual manner. He was when he was writing the paper for his clock, because he was the one that invented the pendulum clock. When he was investigating, researching the clock, he came up with the laws of gravity as we know it, right? So he came up with those in a totally casual manner. And then in another paper, he criticized Newton, that Newton didn't explain gravity, and that he said that that was unacceptable in science. So he wrote a paper on the cause of gravity. It's a
What's
very
the
good
cause of
paper.
gravity?
And
Okay,
unfortunately,
that bridge.
so
What's the
so
cause of gravity?
yeah, exactly. And and it was a very good paper, but unfortunately, I'm not very good in French. I sort of tried to translate it a little bit, but I didn't go far. But I would love to get that translated and get his theories on the cause of gravity. And one thing, for example, his paper on light was ignored for like 200 years. It was rediscovered in the late 1800s, and it's what we use today, like the Huygens principle, for example. But yeah, he was like his work was kind of hijacked by Newton, you know.
Interesting. I didn't know that much about that.
Yeah, and there's a book called The Man of Principles, or The Principle Man. Yeah, that book explains all his discoveries and everything. And what's interesting is they try to say that Huygens had an integrated idea about physics, that everything was mechanical, that's outdated. Like, and what is the alternative? Is magic, right? So right now they're advocating magic, but he said that if we cannot know the principles of how something happens, we might just as well forget about science, because we have to have the conceptions of how things happen in reality. So he in essence he was an objectivist, you know.
Yeah, it's going to have to move forward at some point. If we can't keep up with this nonsense of saying that
Yeah,
information's not available, or in principle information's created at this level.
yeah, like sort of like we are in a virtual reality of some kind,
Yeah,
because
exactly.
now they're trying to push it in that direction.
Oh yeah, they're going
So
deep in that direction.
yeah, like the guy that came up with the Tesla cars, he actually said that maybe we're living in a simulated reality. Like what's his name, Frost. Like his name is like a perfume.
Elon.
Uh,
Elon.
Elon Musk. Yeah, exactly. Yeah, yeah. He came up with that.
No,
So
he has. They have a good line of logic behind it. Do you know? Are you familiar with it? I can give it real quick. It's just that
yeah, yeah. Go ahead. Yeah.
we can create simulations. Eventually, our computer simulations will be very, very accurate. And at that time, we're going to have billions of entities in our simulations. So the likelihood that we are living in some other entity's simulation is much, much, much higher than the likelihood that we're in a real universe. And so that's true, but they forget that likelihood is something that we learn from living inside of our universe, and that we're not in a computer program, that is a concept that we found within our universe. So
Yeah. And from what we can see, from what we can tell, we're not in a computer simulation. We are in a physical world, right?
if it were accurate enough, we wouldn't be able to tell.
To tell the difference. Yeah. But from what we know right now, we live in a physical world, right?
Well, we can use Occam's razor to reduce it, and just the fact that no, it's too ridiculous. It's too ridiculous to say.
Yeah.
We invented this idea of computers, we discovered the idea of programming, and then to say, oh, what if the whole universe is an instance of our technology, is just too bizarre. Too bizarre.
Yeah, it's way out there.
Yeah. But there are people that take it seriously and believe it. Johann Ratz is
Yeah, exactly. He's a huge advocate of that.
He's a nut.
All his videos are on that.
He gets paid to do it, so no surprise.
Yeah, exactly. Yeah, exactly. Yeah, yeah. That's what I thought, because he goes on and on.
Who's he get paid by?
University of California school system, I believe. He's a professor.
Okay.
Okay, that's not surprising.
Yeah.
Yeah, like if you were to engage in an argument with him, he will go on and on and on. You know.
Yeah, it gets outrageous. He was telling me earlier today that we cannot tell the difference between a sense perception that arises from reality and a concept formed in our mind without regard to context and reality. And I said, yes, you can. Now, what's a concept that comes without any information from reality? We call it a floating abstraction in objectivism. But he says it's essentially identical to a concept formed from sense perception, and that there's no real difference between them. And I would say, well, yeah, the difference is one of them is real and one's not, but for him that just means nothing. It just means nothing. But,
yeah, that's like an open door to make things up,
It's a free ticket to fantasy land.
Yeah.
Yeah, I'd be interested what his view is on the concept of right and wrong. Like, what do those concepts mean exactly with his views?
Well, he's a Trump supporter. He believes people should own guns. I mean, he's got real world views, and then he's got scientific views, and never the twain shall meet in his mind. So it doesn't matter what reality is like. He just looks around him in the real world and says, someone might break into your house, you should have a gun. I mean, he just doesn't connect it. It just one of them is his job at the university, and the other is what he does when he gets home from his job. He's a disintegrated. He's a D2. He's a D2 type. So disaster squared. But if either of you know, are either of you familiar with DIM?
Yeah, I am. Yeah, the Peikoff's book, right?
Yeah, Daniel, do you know what I speak of?
Yeah, actually, I have the book, so yeah, I know.
All right, excellent. Yeah, you should look into it. Or the book, I've heard, doesn't contain much more than the videos that the book was compiled from, and the speeches, the talks. So if you don't have time to read the book, just go listen to the speeches 10 times while you're cleaning the kitchen or whatever. It's great stuff, really great stuff. Hey, do we have anything else we want to address from Wolfram? Either of you want to say anything else about what you think or questions or anything?
Like, for example, for example, he sometimes Wolfram, he talks about things that are complex, right? And he equates that to something that is complicated. But I think that something complex does not necessarily means that it's complicated. For example, in the case of complex numbers, usually when you talk to people about complex numbers, they think it's something like hyper difficult. It's something. It's like it's a math that mere mortals cannot understand. But in reality, complex number, it's called a complex numbers because instead of using for describing one thing with one number, you describe it with two numbers or more, right? For example, a point in a Cartesian plot. For example, you have a point and you have two numbers to describe that point in the x direction and the y direction, right? And in 3D, the z direction. So that's all there is to complex numbers, and then how you rotate those numbers around, etc. Like the imaginary numbers I, for example, it's how you rotate those two numbers, you know. So it's complex, but it's not complicated, you know. And for example, and Wolfram sometimes he equates the two as the same thing, you know. It does not necessarily means that it's complicated, that we cannot understand it, but it just means that it has a lot of parts, you know.
Well, I don't know if he's able to prove that it's not reducible, then I think that his point stands that it's complicated, and yet it arises from natural simple rules. That's all he wants to say. It comes from natural simple rules, and we can't reduce its behavior.
Yeah, like we can know the rules, but we cannot predict, for example, a system that's been running on those rules for some time, right?
Yeah, that's it. That's his point, as I see it.
Mm.
But well, all right, gentlemen, we've gone for a couple of hours. I'm not sure if there's anything else you want to cover before we go, but I think that we've hashed it out. I'm sure that as soon as I turn off the camera, they're going to say, "Wait, we didn't cover X, Y, or Z."
Yeah.
But,
like for example, one point is that his cellular automata could be compared to binary numbers, since the program runs on the black cells and white cells, right? So if you can run it that way, you can run it as binary numbers, as normal machine code in a computer.
right.
So that's a point that I thought it was interesting. You can run directly, you know, as a machine code to compute that rule, you know.
I should mention for viewers who are interested, you can get like applets and web browser thingies and stuff where you can write your own rules and see what happens and what they do. Those have been popular for decades, actually, with computer geeks and stuff. But
yeah,
that stuff's available. You can see whether a given rule is complex or simple, and you can monkey with it.
mm-hmm.
People do. So, well, okay. Thank you, gentlemen, for showing up, and we will discuss, I'm sure, the further implications of this in additional hangouts, and it'll come up, you know, as a side note and stuff. I'm sure that there's stuff we missed, and we can hash it out in the near future hangouts.
Okay, thanks for having us.
Yeah, thank you very much for showing up. Thanks, guys.
Yep, good talk.
Everybody, yep.
All right, bye.
Bye-bye.
Bye.